We're going to continue with chapter 11 and section 11.2. This is the only other section in this chapter, but there is a lot in it. So we're going to be looking at two different types of chi-squared tests today. A chi-squared test for homogeneity and a chi-squared test for independence. These two tests are run in the exact same way, and we'll talk a little bit later what the actual difference is between them, but understand that they're the exact same tests on the calculator. All of your steps are going to be the exact same thing. So let's look at this example here, and we're actually going to work through this example, and then we'll talk about the different types of tests. So has modern technology changed the distribution of birthdays? With more babies being delivered by planned C-section, a statistics class hypothesized that the day of the week distribution for births would be different for people born after 1993 compared to people born before 1980. To investigate, they selected a random sample of people from each both age group categories and recorded the day of the week of which they were born. The results are shown in the table on the right. Reason being is they don't schedule C-sections on the weekends. Okay, C-sections are only scheduled during the weekday. So the thought process is that maybe there were more people born during the week after 1993 when they started to do more C-sections than before 1980. So what are two possible explanations for the differences in the distributions of birthday for older and younger people? So one thing is that the day of the week affects birthdays due to C-sections, or C-sections have no effect on the day of the week that people are born, and the difference observed is simply due to random chance. So what I've done here is I found the conditional distributions, or the percentages or the proportions that were born per day for each of these. So 12 over 77, 12 over 77 for these, and then same thing for after 1993. So what we're going to be comparing here is, or what we're going to use here is a side-by-side bar chart to compare the distributions here. So in the kind of purplish color is older or before 1980, our proportions, and then in the pinkish color is the percentage that was born per day after 1993. If we look at these distributions, we can see that the major thing that hopefully is sticking out to you is that the Thursday number has a pretty significant difference for people born before 1980 and people born after 1993. There's not a significant difference in any of the other ones, except there are a fairly substantial difference on both Saturdays and Sundays, with more people being born on the weekends before 1980. So if we talk about those differences, okay, we can see that a higher proportion of older people are born on Tuesday, Saturday, and Sunday, and a much higher proportion of younger people are born on Thursday. This does sort of support the idea that doctors generally plan C-sections for convenient times. There's a smaller proportion of younger people born on the weekend and a much bigger on Thursday, which kind of goes to the idea that C-sections are not scheduled on the weekends and that it is having an impact on the day of the week that people are born. I'll give you a second to write all that. So in this section, what we're talking about here is we're either doing a chi-squared test for homogeneity or for independence. That's different from in the last section when we were doing a chi-squared goodness of fit test. In a chi-squared goodness of fit test, we have what's called a one-way table. We're only measuring the one variable. We're looking at the distribution of a single categorical variable in a population. For example, say I just said, okay, I'm assuming that I want to see is our birth dates or days of the week people are born evenly distributed across the week. That would be a chi-squared test for goodness of fit. Here, when I'm looking at two different distributions, okay, or, okay, is there an association? Are they independent? Do I have two samples? Am I measuring two different variables? That's going to be a chi-squared test for homogeneity or independence. So a one-way table measuring one variable, goodness of fit, two-way table measuring two variables or from two different populations or two different samples, then you'll be running a chi-squared test for homogeneity or a two-way table. How do you rate your problems or your hypotheses? Use the stem of the problem, okay? So oftentimes for a chi-squared test for homogeneity, it'll be something like there is no difference. And then the alternative hypothesis is that there is a difference. So similar like to other types of hypotheses, the null hypothesis assumes that there's no difference. And the alternative, which we're trying to find evidence of, we'll try to find evidence that there is some type of difference, for example, in the distribution of birthdays before 1980 and after 1993. What is the problem with multiple comparisons? What strategy should we use to deal with this? It's important to look at each individual difference when we're looking at the chi-squared test statistic. When we're comparing two or more distributions, it allows for any kind of existing difference to influence the results. And what we really want to focus in on when we're looking at a chi-squared distribution or a chi-squared test is what is causing that chi-squared test statistic to be at the level that it is? What is causing the most significant difference in our results? Different from in the last section, and this is very, very important, is finding expected counts for these types of chi-squared tests. So you want to look at each individual cell. And within each individual cell, you're going to take your row total times your column total and divide it by the overall total. So for example, I'm going to go back to my data set here. If I want to find the expected count for this individual cell right here, I'm going to take my row total, 21, times my column total, 77, and divide it by the overall total of 150. And that will get me the expected count for this particular cell. My observed count was 12, and then I can get my expected count by doing row total times column total divided by overall total. Say I wanted this expected count for this cell right here, Wednesdays after 1993. I'm going to take the row total, 22, times the column total, 73, divided by the overall total of 150, and I'll get the expected count. Similar to in the last section, do not round these expected counts to whole numbers, okay? Keep them to 1 or 2 decimal places. The conditions are the same as the goodness of fit test conditions. Randomness, so either random sample or random assignment. All of your expected counts have to be greater than or equal to 5. And we check the independence condition. When we're doing random sampling, our sample size must be less than 10% of the population size. Chi-squared test statistic is calculated in the same way as the goodness of fit test as well. Take the sum of your observed minus your expected squared over your expected. And it's measuring how far your observed counts are from your expected counts. The higher the chi-squared value, the further your observed are from your expected. Degrees of freedom for chi-squared tests for homogeneity or independence, same thing, are calculated by doing the number of rows minus 1 times the number of columns minus 1. We'll finish this whole example in class, as well as the next one. Sometimes you're asked to run a follow-up test for a test or follow-up analysis for a test of homogeneity. Only do this when asked. When you're asked to run a follow-up analysis, you want to describe the biggest contributor to your chi-squared test statistic and state whether the observed was above or below the expected value. Only do this when they ask you to, and we'll look at that in the example that follows. Now, like I said, there are 2 different types of tests in this section, a chi-squared test for homogeneity and a chi-squared test for independence. They are run in the exact same way. The steps are the exact same thing, same type of hypotheses, same conditions, same test on the calculator, okay? But there is a slight difference in the way that we do them. A chi-squared test for association, or when we're talking about do 2 variables have an association, means that one or both distributions influences the other. If variables are independent, there is no association. There's no influence between the 2 distributions. It is the same test on the calculator, but an important difference. A chi-squared test for homogeneity, you want to think of 2 plus samples that we've taken, and we're measuring 1 characteristic. For independence, we're taking 1 sample, and we're measuring 2 or more variables or characteristics that are involved. When we're writing hypotheses for a chi-squared test of independence, your null hypothesis is going to look something like there is no association, meaning that the variables are independent. The alternative is that there is an association, meaning that the variables are dependent. So you can write it in one of those 2 different ways. Your expected counts are found in the exact same way as we do chi-squared test for homogeneity, row total times column total divided by overall total. And for a chi-squared test for independence, same test statistic, same degrees of freedom, same conditions, everything else remains the same. So there is no real difference between running a chi-squared test for homogeneity and a chi-squared test for independence, both the tests in this section. They are different from goodness of fit, except you want to think of the way we've obtained our sample. That is the key distinction between the 2. So I want to show you actually how to run one of these tests here. Just quickly, how you would go about doing it. Mainly the thing on the calculator. We will go through the full actual tests in class. This is actually related to finger length, which we've talked a little about. Is there, okay, or look at part B, do we have evidence of an association between gender and relative finger length? So basically, do we want to know, is there an association between the gender you are and whether your index finger is longer or your ring finger or so on? So notice here are my observed counts. Okay, they're right in here. Here are the expected counts. Okay, so your expected counts here. And how did I get those expected counts? Well, I've shown you right in here. I've taken my row total times my column total, so 158 divided by 227 over 460 to get the expected counts right in here. Okay, so I found each of my expected counts. You don't need to write this down now because we will go through this example in class, but I want to give you a preview of how to actually enter this data in the calculator. So dissimilar to other sections, when we do this stuff in the calculator, I want to go back up here. Sorry. You need to, and this I skipped over this, but this is important on the top of page 11. You need to enter your data into matrices. So use your calculator 100% when you're running a chi-squared test for homogeneity or independence, but it is a little bit tedious. When you're entering your matrices into the calculator, your matrix size is the number of rows by the number of columns. And to enter your data into a matrix, you go to second and inverse X, which says matrix above it. You're going to enter your observed into matrix A and your expected into matrix B. So going back down to the example we were just looking at about the finger length, okay, I'm going to go to my calculator, and I'm going to go to second and X bar, or X inverse X. Notice that matrix is above that. Then you have to arrow over to edit, and you have to enter your data into the actual matrix. So in matrix A, I'm going to enter my observed data. So hit enter, and you're going to have to change the size of your matrix. So in this particular case here, we're looking at the number of rows by the number of columns for the matrix size. So this would be a 3 by 2 matrix. You do not enter in the totals, okay? The totals don't get entered into the matrix, just the in kind of interior cells. So we have 85, 73, 42, 44, 100, and 116. Okay, and all I've done is I've just entered in my observed data into matrix A. Now you have to find each of your expected counts, which I've shown here. I always like to write my expected counts next to the observed counts, which I've done here. So observed here, now I'm going to go back to second and inverse X, and I'm going to go over to edit, and in matrix B, I'm going to put my observed counts, which I just calculated. Once again, it's a 3 by 2 matrix. So 77.97, 80.03, 42.44, 43.56, 109.41, and 106.59. All right. So now my data is all entered into the matrix. Okay, I had my observed in matrix A and my expected in matrix B. To run the test on the calculator, you're going to go to stat, over to tests. Chi-squared goodness of fit was D. That's what we did last section. Both the chi-squared tests for homogeneity and independence are run on the same way on the calculator, just with letter C. Hit enter. Observed in matrix A, expected in matrix B. Don't have to change anything here. And you would get your test statistic for chi-squared and your p-value there. I wanted to show you this so you have something to reference back to on how to actually use this or enter the data in the calculator. We will run the full test in class, okay? We will do lots of examples for these in class. That's your preview. It's a really important lesson. Chi-square tests are some of my favorite types of significance tests to run. I will see you in class.